Today we're going to shift gears a little bit and we're going to start talking about sequences and series. Let's start off by talking about what are sequences. An infinite sequence can be thought of as a function. The domain of my function, as you see here, are all positive integers, and it's infinite because at the end here we've got this dot 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 that tells us that it just keeps going and going and going. The terms of your sequence will be the values of the function. So it's the a sub 1, a sub 2, a sub n, and you just keep going and going and going. Sometimes you might see sequences written starting with a0, then going to a1, a2, and then continuing on. In some cases, our sequence is going to stop. It's not going to go to infinity, and that's called a finite sequence. It is the first n terms of the sequence. So you can see here we've got a1 through an, and that is our finite sequence. Just like the infinite sequence, you might see this one sometimes written as a0, a1, a2, all the way up to a sub n. So let's look at writing out the terms of a sequence. All that means is that you're going to be doing some substitution. So for a1, that's going to be 3 times 1 minus 2, which is 3 minus 2 and 1. Then a sub 2 is going to be 3 times 2 minus 2, which is going to be 6 minus 2, 4. And let's do a couple more. A sub 3 is going to be, again, 3 times 3 minus 2. So 9 minus 2 is 7. And we'll do one more. A sub 4 is 3 times 4 minus 2, which is 10. You can see that each time we're going up by 3. So the terms of our sequence then are a sub 1, which is 1, and a sub 2 is 4. Then we have 7, 10, and it keeps going and going and going. Okay? Now this one is just increasing by 3 every time. But if we look over here, we're going to have something a little bit different happen with this one. This is a sub, well, let's start with a sub 1. A sub 1 is going to equal 3 plus negative 1 to the first power, which is going to be 3 plus negative 1, or 2. So if you have a sub 2 now, that's going to be 3 plus negative 1 squared. Okay, when we square negative 1, we get a positive 1. So this is going to be 3 plus positive 1, or 4. Now our third term, we're going to get 3 plus negative 1 to the third power. Negative 1 cubed is going to give you back a negative 1. So 3 minus 1 is 2. And if we do the fourth one, you're probably guessing already that it's going to be the same as the second one. 3 plus negative 1 to the fourth power. Negative 1 to the fourth is going to be positive 1. So again, we have 3 plus 1, which is 4. So this is an alternating sequence. We're alternating between the values 2 and 4. And it'll keep going and going and going like that, where all the odd terms are 2's and all the even terms are going to be 4's. So that's one type of alternating sequence. Now let's take a look at another one. Here we have a sub n equals negative 1 to the n over 2n minus 1. So our first term, a sub 1, is going to be negative 1 to the n power over 2, oops, sorry, not n, to the first power, we're substituting in, so that should be a 1. 2 times 1 minus 1, so negative 1 to the first power is going to be negative 1. 2 minus 1 is going to give me 1, so the first term is negative 1. Our second term, squeeze it in down here, is going to be negative 1 squared over 2 times 2 minus 1. When you square negative 1, you get a positive 1, and that's going to be 1 over 4 minus 1, which is 3. So you see we've changed the signs. Term 1, we had a negative, and term 2, we had a positive. So let's see what term 3 is going to give us. I'm going to go up here. A sub 3 is going to equal negative 1 cubed over 2 times 3 minus 1. So negative 1 cubed, we're going to get a negative 1. 6 minus 1 is going to give us 5. And as we continue out with our sequence here, a sub 4, you probably predicted is going to be positive because it's to the fourth power. And then we've got 2 times 4 minus 1. And that's going to equal 1 over 7. So for the denominator, we've got odd integers. And in the numerator, we've got that minus 1 to the n, which tells us we have alternating signs. I know that kind of got squeezed in there weird, but so the minus 1 to the n is alternating signs, and the 2n minus 1 tells us we've got odd integers. So what happens if we're given a sequence, but we're not given the general term a sub n? So we want to write the general a sub n. So start off by looking at what terms you're given. Well, I'm given term 1, 2, 3, and 4. When n is 1, a sub I is 1. When n is 2, a is 3. When n is 3, our term is 5. And then 4 is going to match up with 7. If we take a look, one of the things that we notice right away is we've got odd integers. And how do we write odd integers? Well, it looks like we have the term number n, and we're adding 1 here. Here it looks like we added 2. Here it looks like we added 3. So that's not going to work for writing out the general a sub n. But if we look, if I take 3 times 2, I get 6. If I subtract 1, I get 5. What about if I do 2 times 2 minus 1? That's going to give me a 3. So it looks as though our pattern, a sub n, is going to equal 2n minus 1. Now notice, we call this the apparent pattern. That's because we're only given a couple of the terms. We cannot say for sure if we have gotten the correct pattern. Unless you're told this is the general pattern, you don't know if it's the correct pattern or not, because later on down the line this could change. Okay, let's take a look at another example. We've got the first 4 terms of a new sequence, 1, 2, 3, 4, and those terms are 2, -5, 10, -17. First thing that you're going to notice right away is I've got this alternating positive and negative. So first thing we want to note is we are looking at an alternating sign. So you know that tells you we're going to have -1 to some kind of power. So that means we have -1 raised to a power. But I'm not sure what power that is just yet. Okay? If the second term is negative, then that means that it can't just be -1 to the n. If the first term is positive, it can't be -1 to the n because we would expect it to be negative. So that means that it's most likely going to be -1 to the n plus 1. Let's see if that works. If n is 1, that would give me a positive. If n is 2, that would give me a negative. If n is 3, I would get a positive again. So that part looks all right. Now let's take a look at the differences between our terms and our value for n. As you can see, they're not growing linearly. So let's take a look at what's the next thing besides linear. Well, let's try quadratic. 2 squared is going to give me 4. And if I add 1 to that, then I get 5. And if I want it to be a -5, I'm going to multiply it by -1. And if I follow what I did up here, -1 cubed, let's see if that works for 3. So we'd have -1, n plus 1 would give us 4, so it's going to be positive. And then we have n squared plus 1. 3 squared plus 1 is indeed 10. So we can write our apparent pattern as a sub n is going to equal -1 to the n plus 1 times n squared plus 1. Okay, we're going to look at a special kind of sequence now. This is called a recursive sequence. And what recursive means is that we use the previous terms to calculate new ones. Okay? And you can see that here by looking at a sub k equals a sub k minus 2 plus a sub k minus 1. We're going to explore the recursive sequence using probably one of the most famous sequences. I'm sure you guys have heard of it, the Fibonacci sequence. So we're given the first 2 terms, which we need because we need to go 2 terms back in order to calculate the current term. The first 2 terms are a sub 0. Notice I'm starting off with 0 instead of 1 this time. You can do that at any time. So a sub 0 is 1 and a sub 1 is 1. Let's use those to calculate a sub 2. So I have a sub 2 minus 2 using this formula up here plus a sub 2 minus 1, which is a sub 0 plus a sub 1, which is 1 plus 1. So our second term, a2, is 2. Let's do a sub 3. Using, again, the recursive relationship, 3 minus 2 plus a sub 3 minus 1 is going to equal a sub 1 plus a sub 2, which is 1 plus 2, which is 3. A sub 4, again, we're going back 2 terms, so we're going to use a sub 2 and a sub 3, which were 2 plus 3 and 8. Now for a sub 5, no different. You're doing 5 minus 2 and 5 minus 1. So that is a 3 plus a 4, which is 3 plus 8, which equals 11. And we could keep going and going, but I think you probably get the picture on the Fibonacci sequence. Let's take a look at another example of a recursive sequence. So we're given the formula a sub k plus 1 is equal to a sub k minus 4. So that says I use the current term to get the next one. So to get a sub 2, I'm going to use a sub 1, and I'm going to subtract 4, and that's going to give me 28 minus 4, which is 24. Add 1 to the subscript here, we get a sub 3. It's going to equal a2 minus 4, which is 24 minus 4 equals 20. And one more, a4 is going to be a3 minus 4, which is 20 minus 4 equals 16. So that's another example of a recursive sequence. Okay, now we're going to shift to a new topic, and we're going to talk about what are factorials. So n factorial, that's how we say this symbol, is the product of all the positive integers that lead up to n. So in this case, 2 factorial is going to be 2 times 1, which is just 2. 5 factorial is going to be 5 times 4 times 3 times 2 times 1, and that gives me 20 times 6, which is 120. There is a special case. 0 factorial is defined as 1. Otherwise, they all follow the same pattern of going starting with n and multiplying all the numbers down to 1. So let's take a look at an example. We've got a quotient here, 8 factorial divided by 2 factorial times 6 factorial. So let's write out 8 factorial. We have 8, times 7, skipped a few there, times 6, times 5, times 4, 3, 2, 1, all the way down. Divided by 2 factorial, which is 2 times 1. And then we've got 6, 5, 4, 3, 2, and 1. Now if you take a look, in the numerator, I've got a 1, and in the denominator a 1. 2 cancels 2. 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So that means I'm left with 8 times 7 divided by 2, which is just 28. Another way that we could write this, if you look, we ended up canceling 6 factorial, right? So what we could do is, instead of writing out all those terms like we did, we can write 8 factorial over 2 factorial times 6 factorial is equal to 8 times 7 times 6 factorial divided by 2 factorial times 6 factorial. And then you can see your 6 factorials cancel out, and again you're left with 8 times 7 over 2, which is just 28 once again. Let's look at another example of evaluating factorials. We'll be working quite a bit with the factorials when we get into class next time. Using the ideas from the previous example, if I write out n factorial, it's going to be n times n minus 1 times n minus 2, and you keep going and going and going like that. Divided by, again we keep counting down, n minus 1 times n minus 2 times n minus 3, and you'll keep going and going. We can think of this as, instead, we know now that these terms are going to cancel, and they're going to keep going and just keep canceling out all the way down. So we're going to be left with just n. So another way that we could think about this problem is writing n times n minus 1 factorial over n minus 1 factorial, and now we can see that those cancel out, and we're left simply with n. Next topic we're going to discuss is series. A series is a sum of a sequence. So we've got a sequence A1, A2, A3, all the way up to A sub n. So this is a sequence where they're separated with commas. Now if I add all these values up, like you see here, this is a finite series. One convenient way to write series is using summation notation. That's this symbol here that you see. This is called sigma. And this I down here is called the index of summation, and you see that I is present here too. So that's called the index of summation. The 1 is called the lower limit. Of the summation. And the n is the upper limit of the summation. And again, A would be your terms. Just like with sequences, we can also have infinite series, and that's where your upper limit is infinity. So you can see, just like before, we end with that ... to tell us that it keeps going and going and going. And yes, we will find some ways to actually sum those infinite series. So let's practice writing some series in summation notation. If we look here, we've got 1 over 3 times 1 plus 1 over 3 times 2, 1 over 3 times 3, and it keeps going, and then our last term here we have 1 over 3 plus 9. So if we take a look here, we've got 1, 2, 3, and then it's going to be all the way up till 9. This number is going to be your index. So we've got the sum, and I is going from 1 all the way up to 9, and our a sub I is going to be 1 over 3 times n. So this is the series in summation notation. Let's not look at this example. That was on the wrong slide. Sorry about that. So let's do another example of writing a series in summation notation. So let's say you have this series 5 over 1 plus 1 plus 5 over 1 minus 2 plus 5 over, oops, sorry, that's plus 2, 1 plus 3, and we're going to go all the way up to 5 over 1 plus 15. So we can identify right away, this is going to be our n, that's going to be our variable. So if we get sigma, and then our index I is going from 1 to 15. And our terms are 5 over 1 plus I. And this up here should also be an I, not an N. Okay. Because you want your index here to match whatever your variable is here. And it doesn't always have to be I. If we look at this example, we've got 1 plus k squared as k goes from 3 to 6. So let's write out these. Notice we didn't start at 1. We don't have to. We can start at 3. So the first term is 1 plus 3 squared. Second term is 1 plus 4 squared. 1 plus 5 squared. And 1 plus 6 squared. That gives us 10 plus 17 plus 26 plus 37, which is going to equal 90. Okay. So a few properties of summation notation. If you have the sum from I equals 1 to n of a constant c, that's just going to look like c plus c plus c, and you're going to sum it n times, so it's c times n. Another rule of constants, this is called a constant sum. Okay, another rule of constants is if you have a sum where you have a constant times each individual term, you can factor that constant out, do the sum first, and multiply the result by the constant. Two more properties of summation notation. You can split sums and differences. So if you have the sum of A plus BI, you can split that into two separate pieces, sum A, sum B, and then add them together. Same thing with subtraction. We've got A1, we've got A, the sum, minus the sum of B's. Okay, so how do we find the value? How do we find the sum of a series? Take a look at our first example. We've got I equals 1, I is equal to 1, all the way up to 3. So if we start substituting, we've got 3 over 10 to the 1 plus 3 over 10 squared. And my upper bound is 3, so 3 over 10 cubed. What does this look like? This is called a partial sum because I'm limiting it to the values 1 through 3. We've got 3 over 10 is going to be 3/10, so 0.3. And then we've got 3/100ths and then 3/1000ths. So 0.3 plus 0.303 plus 0.003, and your sum is 0.333. Next, let's take a look at an infinite sum. So we're going to do 3 over 10 to the first plus 3 over 10 squared. And what's going to happen here is you're going to see a pattern develop. Oops, that should be 3 over 10 to the fourth. Okay. When I did the first 3 terms, I got 0.333. Now if I keep going, I'm just going to keep putting additional 3's on the end. That is equal to 1/3. So we've just taken the sum of an infinite series. Let's do one more application problem. So we're going to look at population. For the years 1980 to 2003, the population of the United States can be approximated by A sub n equals 226.9 plus 2.05 n plus 0.035 n squared. And n is going from 1 up to 23. N equals 0 will correspond to 1980. And it says we want to find the last 5 terms. So let's start off by identifying what the last 5 terms are going to be. 23 is the last term, then 22, 21, 20, and 19. So 1, 2, 3, 4, 5, the last 5 terms. Okay, let's start off with finding A19. So that'll be the 19th term. And you get 226.9 plus 2.05 times 19 plus 0.035 times 19 squared. And if you put that in your calculator, you'll get about 278.5, and that's the population in 1999. If we keep going, A sub 20. So this is going to be the population in the year 2000. Oops, 226.9 plus 2.05. And now we're going to substitute 20 because we're looking at the 20th term. And that's going to be approximately 281.9 million people. And if we do the same thing for 21, 22, and 23, we'll see that 21 is 285.4 approximately. 22 is about 288.9, and 23 is about 292.6. And that would correspond to the 2003 population, 2002, and 2001. Okay, here's some problems for you guys to try at the end of section 9.1. Problem 8, 10, 38, 78, and 90. Give you a second to write those down. Okay, great job everybody, and we'll see you in class.